In this video, we discuss about expectation, correlation, and covariance of multiple random variables. These two terms, correlation and covariance, are specific terms associated with multiple random variables. Now we consider expectation of function of two random variables. To do that, just I write the function of single random variable and its expectation. Suppose for a single random variable, the equation is expectation of gx is equal to integral minus infinity to infinity gx fx x dx. It means we are multiplying the function with its PDF and integrating between minus infinity to infinity. The same thing can be written for function of two random variables. So here gxy is a function of two random variables. Now expectation of gxy is equal to integral minus infinity to infinity integral minus infinity to infinity gxy fxy xy dx dy. In place of single function, we are substituting the function of two random variables. In the place of single PDF, we have joint PDF in this equation. Now we consider a function gxy is equal to x plus y. Now for this, we want to evaluate expectation of x plus y. Now expectation of x plus y, as per the definition, we substituted in the double integral and we have written x plus y in the place of function and we have joint PDF. Now if we expand this, we will have double integral x into its PDF plus y into its PDF. Therefore we can write it as expectation of x plus expectation of y. Therefore expectation of x plus y is equal to expectation of x plus expectation of y. Therefore it is a linear operation. Now we discuss what is correlation. EXY is known as the correlation of random variables x and y. It means expectation of product of x and y is known as correlation of random variables x and y. Now I substitute the values here. Expectation of xy is equal to double integral xy fxy xy dx dy. This is joint PDF. And now if x and y are statistically independent. In the previous videos, we defined what is statistically independent random variables. If two random variables x and y are statistically independent, then its joint PDF is given as the product of the individual PDFs. I'll write it here. The joint PDF is equal to the product of marginal PDFs or single PDFs. This is true when x and y are statistically independent. Therefore, if I write this equation in the place of joint PDF and separate the terms under the integrals and rearranging the terms, I get expectation of xy is equal to ex ey. Therefore, the correlation of two random variables, that is exy, is equal to ex ey if x and y are statistically independent. And one more point here is, if exy is equal to 0, that is correlation is 0, then x and y are known as orthogonal. One has to remember these terms. If exy is equal to 0, that is correlation is 0, then x and y are known as orthogonal random variables. Now what is covariance? Covariance of random variables x and y is given as expectation of x minus mx and y minus my. In the previous videos, we have seen variance as a broad measure of the deviation of random variable from its mean value. If you remember, variance x is defined as expectation of x minus mx whole square. That is the deviation of random variable from its mean value. In case of two random variables, covariance is deviation of random variable x from its mean value into deviation of random variable y from its mean value. Now if we expand this product x minus mx into y minus my, we get 4 terms, and simplifying them we get expectation of xy minus mx into my. What is mx? Mx is nothing but the mean value. My is nothing but the mean value of y. Therefore, the covariance of two random variables is exy minus mx my. If x and y are statistically independent, then we know if x and y are statistically independent, it is exy is equal to ex into ey. Therefore, substituting this in the place of exy, if I substitute ex into ey, then this reduces to 0. So if the random variables x and y are statistically independent, then covariance of xy is equal to 0. This is very important result. Now we make some observations on covariance. If x and y are statistically independent, then covariance becomes 0. That we have seen. Covariance xy is equal to 0 if x and y are statistically independent. And one more observation is, if covariance xy is equal to 0, then x and y are uncorrelated. This is very important point to remember. And then, but the converse is not true. That means if x and y are uncorrelated, they need not be statistically independent. So the converse is not true. But if covariance xy is equal to 0, then xy and are uncorrelated. Properties of covariance. Suppose if I consider covariance of single random variable. In fact, we define covariance for two random variables or more. But here, if I substitute single random variable for covariance definition, then we have covariance xx, and if we substitute the equation, then we get ex square minus ex whole square, and this is nothing but variance of x. Therefore, if we apply covariance definition on single variable, then it becomes variance x itself. And then the second property is covariance of x plus a y plus b is equal to covariance of xy. At this point, we recollect that variance of x plus a is equal to variance x for a single random variable. This we have seen. If you are changing the random variable and adding a constant here, the mean value of this also is shifted by the same amount. Therefore, variance won't change. So in the case of two random variables also, if you add two constants here, the mean values are equivalently shifted and there is no change in covariance value. And the third one is covariance is a bilinear function. We can verify this property. Suppose if you consider covariance of a1x1 plus a2x2 comma a3x3 plus a4x4, then if you substitute these values, then we get this result. How can we understand this? You take product of these two terms here, a1x1 into a3x3. Therefore, the first term would be a1 a3 covariance x1 x3. Similarly, you consider this term and this term, you get a1 a4 covariance x1 x4. And then a2 x2 into a3 x3, we get a2 a3 covariance x2 x3. And lastly, a2 x2 into a4 x4, we get a2 a4 covariance x2 x4. This we can verify. So these are the three important properties of covariance. Define correlation coefficient. The correlation coefficient is defined as covariance xy by sigma x sigma y. It is indicated with a letter rho. Rho is equal to covariance xy by sigma x sigma y. Sigma x is nothing but the square root of variance x. Similarly, sigma y is equal to square root of variance y. They are known as standard deviations. Sigma x and sigma y are known as standard deviations in statistics. Therefore, the correlation coefficient is given as covariance xy by the product of the standard deviations of x and y. The correlation coefficient is a measure of the correlation between two random variables. Now, if you observe, this value rho lies between -1 and 1. The value of correlation coefficient always lies between minus and 1. We further discuss in the next slide about correlation coefficient. Now we make some points on correlation coefficient. We've seen that correlation coefficient rho is defined as covariance xy by sigma x, sigma y. Now if rho is equal to 0, then this covariance xy becomes 0. If covariance xy becomes 0, then we know that x and y are uncorrelated. That means correlation coefficient gives us whether two random variables are correlated or uncorrelated. If rho is equal to 1, it means x and y are highly correlated. It means y is equal to ax plus b. They are very highly correlated. Y is linear function of x. And now, if rho is equal to -1, again they are highly correlated with the difference that y is linear function of x but with a negative sign. So therefore we observe that correlation coefficient gives us whether two random variables are uncorrelated or correlated. Now to conclude, in this video we observed expectation of multiple random variables, and then we defined what is correlation, that is expectation of x and y, and then we defined what is covariance, and then we discussed certain properties of covariance, and finally we also defined correlation coefficient with which we can find out whether two random variables are uncorrelated or correlated.